In this video, we're going to take a look at proving de Moivre's theorem by induction. So they could just say it like that in the exam, and if they do, you'd have to go to your log tables and you'd have to look up de Moivre's theorem just so you know what you're trying to prove. You should know what it is off the top of your head anyway, but it is in the log tables. I'll tell you the page now, on page 20. So on page 20, it says that if you have or by cos of theta plus I sine of theta, and you raise all of that to the power of n, we're trying to show that it's equivalent to or to the power of n cos n theta plus I sine n theta. So that's our goal. So, like all proofs by induction, what we're going to do is step 1, we're going to prove that it is true for n is equal to 1. For this, I'm going to set it up as left-hand side and right-hand side. So, my left-hand side here is going to be r to the this, so we're going to have r cos theta plus I sine theta, all to the power of 1. And if you raise anything to the power of 1, it's just itself. So you're just going to have r cos theta plus I sine theta. Nice and simple. If you raise something to the power of 1, it's just itself. For the next one, what we have is we have to fill in n for 1. So we're going to have r to the power of 1 cos, and instead of n, replace it with the number 1. So 1 theta plus I sine of 1 theta. R to the power of 1 is just r. Cos of 1 theta is the same thing as saying just theta. Plus I sine of 1 theta, well, that's the same as saying I sine of theta. Don't need the 1. Now, if I take a look at what I do have that the left-hand side matches the right-hand side. So I can say left-hand side equals right-hand side. Therefore, true for n is equal to 1. The next step is the same as all proofs of induction or proofs by induction, is to assume true for n is equal to k. So we are going to assume true for n is equal to k. And what I'm going to do here is I'm going to replace all of the n's up here with k. So I'm going to speed things up here. Rather than me writing it out again, I'm just going to bring it down. And I'm going to replace all of them with k. You'll have to write them out in the exam. So I'm going to replace all the n's with the letter k. I might even just use a different colour so we can keep track. So n is equal to k. So let me fill in purple here all the k's. So there was an n here, it now is a k. An n here is now a k. K there, and another k there. Now, that's the second step done. It's nice and short. We're assuming that it is true for that. For step 3, we're back to proving. So we're going to try and prove that it is true for n is equal to k plus 1. So we have a bit of work to do here. And my tip to you is whenever you're trying to do a step that involves the word prove, you should always split it into left-hand side, right-hand side. So left-hand side here, and I'm going to do right-hand side here. And we're going to need a good bit of workspace between them. So I'm going to spread them out. So in this instance, for the left-hand side, I'm actually replacing all of the n's, which in the above step were k's. I'm taking out all of the n's here, which was k before, and I'm replacing it with k plus 1. So I'm taking out that, and I'm putting in k plus 1 up here. For the right-hand side, just to make it ultra clear, look, I'm taking the right-hand side here, this, and I'm going to replace all of the n's there again with k plus 1s. I'm going to do the same thing, but I'm going to take out all the n's, and I'm going to replace all of those n's with k plus 1. So I'm going to need a little bit more space here, and a little bit more space here. So I'm filling in k plus 1 and k plus 1 again here. Now, I want to show that these two sides when I have all my k plus 1s filled in for all of the positions of n, which was an n here, an n here, an n here, and an n up here. I want to show and work out using algebra that these two sides are going to be equal. First thing I'm going to do is I know that if I can get step 2 into step 3, I know I've got that high partial credit. How I do that is whenever you see something plus 1, you always know what you're going to do is use your index laws or your laws of indices to change this into r cos theta plus I sine theta to the power of k multiplied by r cos theta plus I sine theta, so plus I sine theta to the power of 1. Because I'm just using the fact that if you've added them, that's in indices, that means that you had the same base and you multiplied them. That's all I did there. Now what I'm going to do is I'm going to say, right, I actually said in the previous step, I said I assume that this is actually this. So I said it in the last step. This, which I have down here, is actually this. So I'm going to replace all of that with the above. So let me cheat a little bit here. I'm just going to copy it. So I'd rewrite it out. What did I say it was in step 2? So there it is. And then I'm not going to forget that what I have to do is I have to multiply it by r cos theta plus I sine theta. So I'm going to multiply that by r cos theta plus I sine theta to the power of 1, which remember is just 1. Now, what I'm going to do is I'm going to take my time multiplying these out, and what I'm going to have is I'm going to do the r's together because everything's multiplied. And remember, multiplication is commutative, it's also associative and distributive, and I can use all of those rules from first year to play around with this and make this question a little bit easier. So I'm actually going to multiply r by r to the k. That's r to the k, that's r to the 1 if we put a power on it. If I multiply those two, I'm going to get r to the k plus 1 at the start. Now I'm going to multiply out, bit by bit, my two brackets. So I've done the r parts, those can go to the front. Now I'm going to do cos of k theta by cos of theta. So it's by cos of theta. So let's write them side by side like that. Now I'm going to have cos of k theta, which, just to help us, that came from the blue part, and this came from the green part. Okay, let me give it a different colour. That came from the green bit. Then it's going to be plus, we're going to do cos of k theta multiplied by I sine of theta. So I'm going to put the I at the front, and then I'm going to do sine of theta. Remember, multiplication is commutative. It doesn't matter what order I do it in. I'm going to put the I at the front so I can kind of signal early on when you're reading it that that's an imaginary number. That's again from the green part, those two pieces, and then from the blue part. Okay, now I'm going to do this. So I'm going to have plus I sine of k theta from the blue piece multiplied by the first part here, which is going to be cos of theta from the green piece. And then we've one more to go. I'm going to have I by I, which is I squared, and then I'm going to have sine of k theta from the blue part, and then I'm going to have from the green piece, I'm going to have sine of theta. Now, I'm going to tidy this up as much as I can. And what I notice is that there's an I squared jumping out at me. And what you'll hopefully know and remember is that whenever you have I squared, it's equivalent to minus 1. So I'm going to rewrite all of this out. And what I'm going to do is I'm going to change that I squared into a minus 1. Okay. So I'm going to say that that's minus 1 times this, which just makes this negative. Now, the next part. I need to gather my real and my real and my imaginary and my imaginary. So I'm going to say all of my real stuff are the things that don't have an I. So this is real. because there's no I involved. And this is real. There's no I involved. So I'm going to write those together down here. So I have cos of k theta, cos of theta. Take away the other real part, which is sine of k theta, sine of theta. Okay, so that's the real parts together. And let's not forget that I'm multiplying by r to the k plus 1. I'm then also going to have, on the outside, or the next part here, I'm going to have my imaginary numbers. So there's my two imaginary numbers. So I'm going to say I, factorize out I as common, right? So I don't have to write it twice. We've got cos of k theta, sine of theta, plus sine of k theta, cos of theta. So I've grouped my real and my imaginary all there. Okay. And I have that as well. Right. Okay. Now, if you go to your log tables and you go and you look up on page, I believe it's page 14, what I'm actually looking at here is this is actually cos of some angle times cos of a different angle. Let's call it B. So cos of A by cos of B. Let me write it underneath. Cos of A, cos of B. Take away sine of that same angle, the same angle I called it A the first time, times sine of another angle, sine of B. And if you look on page 14, they're telling me that that's equivalent to saying cos of A plus B. So I can replace that pink part instead. All of that is actually cos of A plus B, where A is actually going to be k theta plus B, which is actually theta. Okay. You can apply the exact same thing to the next guy over here, where this is going to be cos of A again, sine of B. This is going to be sine of A, and this is going to be sine of B. And if you look at that on page 14, directly under cos of A plus B, we've got sine of A plus B, which goes, now cos of B, sine of A, but look, that's the same thing, it's commutative. And then cos of A, sine of B, sorry, that should be cos here, apologies, that's a cos. Those guys are commutative. So this can all be replaced with plus sine, and it's an I, let's not forget our I, so sine of k theta plus theta. So I'm using page 14 again, sine of A plus B is what all that bubbled down to. Now if I look at this and I actually tidy that up further, I can factorize out the theta, and I'm going to have cos of theta by k plus 1 plus I sine of theta by k plus 1. And all of that is multiplied by r to the k plus 1. Now, if I go back up now and I zoom back out and I look at what I wanted. I wanted r to the k plus 1, I wanted cos of theta by k plus 1. Now I have k plus 1 by theta, but guess what? Multiplication is commutative, it's the same. So I now have shown that my left hand side equals my right hand side, and therefore I've shown that it's true for k plus 1, provided true for n is equal to k, since it is true for n is equal to 1, we showed that in step 1, remember, since it is true for n is equal to 1, it is true for n is equal to 1, and then 1 plus 1, which is 2, and then 2 plus 1, because it's true for 2, so it's true for 3, And we can say, and all values of n that are natural numbers. And that's it. Start to finish, there's our proof of de Moivre's theorem. Okay? So you shouldn't need to learn it off by heart. It's the same as any proof by induction, and they could spring really any sort of proof by induction on us. So know the steps, and then at this stage what I used was the trig identities. Okay, so if you're not sure on this step to this step, make sure you go back over your trig identities.